You're live, Ray. It's green and red.
Christmas.
Means we're on. We're on. So, y'all know I don't care if you get on there live or not. I'm just doing it just for that option. First hour, I do the same thing. When I get done and I hit done, it's on there forever for you guys to view whenever you wish to. So somebody in first hour, they just asked me if I do it that way. So here I am, I'm live. And apparently there are 7, oh, now there's 6. Hi, guys. So I got 6 others decided they want to do it. I don't check roll that way. I mean, I don't care. Fair enough. The only people I check roll are the people that are supposed to be here. I count you guys here. So the second half, I don't count them absent. Test day I did, because that was easy to do. Oh, now I'm just down to 4. As soon as I heard that, they said, oh, that's really fun. So we're there. That I need, that I don't need, this I don't need, this I don't need, this I need. All right. How is everybody? Everybody all good? Happy, happy, joy, joy. Rest of this semester. There are 2 main topics we're going to be discussing. One of them is confidence intervals. What we talk about today, we're going to talk almost exactly the same thing on Wednesday. We will talk almost the exact same thing in chapter 9. No, we will not. I'm sorry. Chapter 10. Chapter 9 deals with hypotheses testing, so that's the other inference we need to talk about. If you can understand what we're going to do here, these confidence intervals, then the rest of it's going to be very, very simple because there's not much difference. Okay, with all that stuff. So I'm going to make sure that we get this today. I think I really like the way that it flows. Hopefully you did get to watch 8-1, or you at least read 8-1, or at least got some notes out of that and understand a little bit out of 8-1. I'm going to emphasize some of the things out of 8-1 that come up here today, just to make sure we get it. Talk to me.
Can you go over the difference between interpreting confidence intervals?
I'm going to hit that today.
Okay.
There are 2 major mistakes that students always make, and that's one of them. And so hopefully by the time we get done with it today, it will not happen. But I will for sure hit that today. If you are watching it live and you have a question or something like that, all I'm asking you to do is just text your buddy and have them ask it for you. That seems to be the best way, because I can't see if you have any questions. Anyway, and if you're not watching it live and you have a question, just email me and I'll answer it then. Y'all okay with all that stuff? The best way I have it going, I think. I don't know. If you got a better idea or you got something that you think works better, please let me know. By the end of this lesson, hopefully, we can state and check the random, the 10%, and the large counts conditions. In fact, you already know these. We just got to make sure we do them for constructing. Determine a critical value. This is the second mistake that students make. Construct and interpret a confidence interval for population proportions and determine a sample size that's needed. Here we go. All right, guys. In life, very rarely do we know what the population average is. Very rarely do we know what it is. We do not know per se what percentage of cars are white. And we could I think there is a calculation for that. We do not know the percentage of M&Ms that are blue, although Mars claims that there's a certain percentage that are blue, but we do not know it. Sorry. So in order to find or to figure out what that is, we take a sample. Let's say we took a sample of US households and I found out that 47% of those samples or those households owned a dog. Fair enough. We think that that's probably not too far off. Is the value of the entire population going to be 47%? Probably not. Probably not. If I took another sample, is that going to be 47%? Probably not. In fact, I'd be surprised if all three of those were the same, right? Because we know we have some sampling variability. So our big question is, if we took another sample, would it be 47%? How close do we think that 47% is to the population? Well, most of the time we don't know what that is. We don't know what the population is. We hope it's really close, but sometimes we don't know. So we have a little bit of wiggle room in there that's going to make us play with that. That's what this interval is going to give us. We're going to calculate some interval, and we really think that the population average is inside of there. We think that it is. That's what we're going to end up doing today. Fair enough? Confidence intervals. Here we go. This is off of 8.1. It specifies a range, an interval, right, of plausible. And hopefully in 8.1 you saw the difference between plausible and possible. Okay, it gives me a plausible values to estimate some unknown parameter. Okay, some unknown parameter. We know what a parameter is, right? That's a population average. So that's what this interval is going to give us. All right. We're going to use sampling distributions to help us out with this stuff. I thought that was going to be more helpful to us than it's not. Here's a formula. Here's a formula. Now, understand this. Throughout this chapter, next chapter, I'm going to give you a lot of formulas. There's going to be kind of a generic formula, and we have to convert that formula. So this formula is written in words. You're going to have to convert that words formula into a variable formula. Okay? Here it is in words. Statistic plus or minus critical value, statistic plus or minus critical value multiplied by the standard error of the statistic. That's what written in words, guys. You're not going to write it down in words. You're going to write it down in variables. So I'm going to go through each one of those, and we're going to turn it to a variable, although I think you already know what these are. Just so you know, I have this link to the formula sheet. And if you go down to the bottom of the first page, you will see confidence interval, statistic, plus or minus, critical value, standard error of the statistic. So it's written in words right there at the bottom. Okay? So by some crazy chance, if you ever forget it, which I would be very, very surprised if you did. We haven't talked about this word standard error a lot. We use standard deviation. Okay, standard error. What standard error is and the difference between standard error and standard deviation is when the standard deviation of a statistic is estimated from a data. It's estimated because the only way to know the standard deviation is you have to know what mu, or you have to know what the population average is. We don't know what the population average is. If we knew what the population average is, we wouldn't have to do a confidence interval. Fair? So when we have to estimate what that population average is, then they're going to call that a standard error as opposed to the standard deviation. It's just a terminology. In fact, I will still probably use standard deviation a lot. If you catch me doing that, please try to correct me and say standard error. Okay, standard error. Standard error. No big deal. It's not that big of a deal. I just wanted you to understand. If you see standard error, basically that means we don't know the population. And I think it'll make sense to you in just a second. Ooh, I'm live. You just told me that. All right. So let's go through each one of these as a variable. Statistic. I think you already know what a statistic is, right? Statistic comes from where? Where does a statistic come from? Sample. Good enough? Right? Statistic comes from a sample. So if we are talking right here, statistic comes from a sample. If we are talking proportions or categorical data, then that statistic will simply be p hat. That statistic will simply be p hat. I think we called it some type of an estimator, a point estimator, or something like that. I think in 8.1, they called it a point estimate or something like that. If it happens to be numerical data, then that statistic will be X bar. You will not see X bars or means until chapter 10. We're in chapter 8. So chapter 10 is when you will see that. So we know what that statistic is. In this chapter, it's going to be p hat. It's going to come from this sample. It's going to come from your sample. Question there, we okay? Happy, happy, joy, joy. Plus or minus. Critical value. Okay. Like I said, I thought you guys are two big mistakes. One of the big mistakes was what was asked earlier. This is the second big mistake, the critical value. It is the z-score associated with that level. It's the z-score associated with that level. We'll spend a couple more slides on this later on to help us out a little bit more. Typically, that level will be given in the problem. 95%, 90%, 88%, 96%, 90%. It will be given in the problem. If it's not given in the problem, just use 95%. If it's not given in the problem, use 95%. All right. Everybody good? Anybody watching? Tell me if they're watching now. Who cares? Pencils going. All right. Standard error of the statistic. You already know what this one is. Square root. P, 1 minus P over N. What's different about this one than the one we were given last chapter? Y'all see the difference between this one and the one last chapter? It's subtle. What's the difference? Who sees it? Come on, you talkers. Talk to me.
Uses p hats.
Uses p hats, right? Last chapters, it didn't have the hats. Why do we have the hats? Because we don't know the population, right?
Wait, but if the statistic is a mean, why are we still using p hat?
Okay, so if it's means, it won't be.
Okay.
Fair enough. So that's a good question. So this is not going to be means. All this whole chapter is proportions. This whole chapter is proportions. If it's means, it's a completely different formula.
Okay.
Good question. So, and guys, here's why they call it a standard error instead of a standard deviation, is because of the hats. We're having to estimate what the population standard deviation is. And we're using an estimate from the sample. So because we're estimating from the sample, we have p hats. That's why they call it the standard error. Again, real quick, let me just kind of show you on this. And maybe you noticed it on the formula sheet last time. If I go down to the next page, it says sampling distributions for proportions. And here's the mean, and here's the standard deviation. And then over here, it says standard error. And it's the exact same thing as this, other than it used p hats. And so when you go back up to the formula and it says standard error of the statistic, here's the standard error of the statistic. And so we can see that right through here. Okay? So it's on your formula sheet, but it's not. All right, loading. Boom, boom. Why are we using p hat instead of p? Because it's a sample, it's not from the population. All right, everybody good? Now, here's what the formula looks like in variables. Okay, in variables, it says p hat plus or minus z. They put a little asterisk by it. I don't care if you put the asterisk by it or not. If you see the asterisk, you do, and if you don't, you don't. And AP will not count you right or wrong if you put the asterisk there or not. And then the standard error, which is p hat, 1 minus p hat over n. We know what the z is. We know what the standard normal curve with confidence error between negative z. This is called one sample. I call it a one sample proportion z interval. You need to know those words. One sample proportion z interval. They call it a one sample z interval for proportions. So I abbreviated it just a little bit. One sample proportion z interval. Woo-wee! All right. All right. So far, the only couple things we got out of this is the formula. Hopefully you've got the formula down. If you can't, hopefully you know where to get it from. All right. Big time deal here. Because there's 3 parts to that formula, the statistic, the critical value, and the standard error, there are 3 conditions that must be met in order to calculate this formula. Not only must these 3 conditions be met, but they must also be checked, and you must show that you have checked them. So there's the formula. I want to make sure we understand how we know that we can check this p hat. And you can check this p hat because we know that it is a random sample. It is a random sample. Be sure that p hat is a valid point estimate. We know it's a valid point estimate if it came from a random sample. The data must come from a random sample from the population of interest. It has to be a random sample from the population of interest. It must be random. It must be a good point estimator. That's why we have a p hat right here. If it's not a good point estimator, there's no point in doing this. Random sample. All right. Good. Z. How do we know if we can use Z? It must be large enough to say that we can use a normal distribution or an approximate normal distribution. So the large counts condition. When the large counts conditions are met, we can use a normal distribution to calculate the critical value Z. We don't know the value of P, so again, we will be using P hat. We want N times P hat to be greater than 10, and we want 1 minus P hat times N to be greater than or equal to 10. Same condition we used last chapter. Same condition we used last chapter. Large counts. Hey, mistake. Don't be late again. Yes, sir.
Yes, sir.
And you know you'll get told on quick. Even if it's not your fault, guess what? It's your fault. I found out good information about Charlie. Condition, okay? The last one, the third condition. How do we know we can use that one? Do you remember? 10%. Your sample must be less than 10% of the population. Our sample must be less than 10%. Of the population. When we are sampling without replacement, that's what's key too. If you're sampling with replacement, we don't need to check the 10%. If we're sampling with replacement, we don't have to check the 10%. It's only without, which is nearly always. It's nearly always without replacement. Woo! 3 conditions. Very, very, very important. We meet them, we check them, and we explain that we check them. The large counts. We must show the N times P hat, and if we can show that, approximately normally distributed, and that's important. We must show that P hat came from a random sample. And we must show that our sample size is less than 10% of our population so that we can use this formula. All right, here we go. I think. Oh, it's the same thing. Random 10% large counts. Bam. How do we get the Z star critical value? Very important. This is probably, like I said, this is one of the biggest mistakes that students make on this Z star critical value. Okay. To find the critical value for a 95% confidence interval, we need to understand that at 95% is the middle 95%. It is the middle 95%. Finding the critical value for a 95% confidence interval starts by labeling the middle 95%. I need this Z-score and that Z-score. I need both of those Z-scores. So here's what I need to know. If that middle is 95% and the whole thing is 100%, then that leaves 5% left over, and that leaves 0.025 on each end. It's very important that we know that. And now what I have to do is find this Z-score that goes with this area of the 0.025. And we're going to do that one of 2 ways. Well, here's the area. There's that middle 95%. That leaves 0.025 on both ends. I need that Z-score and that Z-score. What's ironic is this Z-score and this Z-score are the same. In fact, actually, hold on. If it's 95%, don't we know that Z-score already? That's 2 standard deviations, right? So really it's 2 and -2, except we want to be a little bit more precise. The empirical rule is rounded. So here's what we're gonna do. You're gonna use table A if you want to. And in order to use table A, it's confusing because we have to go through this whole thing right here and find 0.025. 0.01, 0.02, 0.017. This is 0.022, 0.017, 0.0127, 0.0127, 0.02. Ah, there it is right there, 0.025. Right there. Negative 1.95. 6, wrong column. Negative 0.96. That's nice because what's that going to make this z-score? 1.96. So 2 is close. Y'all okay with that? Remember how the formula shows p hat plus or minus. And so that's why the plus and the minus comes about. If we don't like looking it up in the table, which I don't think anybody does, then what we have to do is look it up on our calculator. And if I look it up on my calculator, here's my calculator, clear, second distributions, and we go down to inverse norm. And that's where we'll punch in that 0.025. 0, 1, because I'm looking for the z-score. Is that my door? And there's that negative 1.96 or negative 1.95 if you want to be a little bit more accurate. I said a lot of students mess up on this. When they want to find the 95% confidence interval, I'll see inverse norm of 0.9. That won't get it. It's not 95th percentile, it's the middle 95%. Now, I'm pretty lucky on my calculator because I can do second distributions and go inverse norm. And I actually can put in 0.95 because I have a middle button. So if you have a middle button, we don't need to worry so much about the tail because it will give me the negative and the positive. And so some of you have updated calculators enough to where it will do that for you. Kind of follow along with that. Question? Y'all okay? Hope you understand why students make a mistake on that. All right, if they want the 88 confidence interval, 88% confidence interval, then that means it's the middle 88, which leaves 22 left over, which puts us at, not 22, 12, which puts us at 0.06 and this at 0.06. And so if I want the z-score, confidence level of 88%, I have to do inverse norm of 0.06. And that will give me that negative z-score, and then I can just turn it into the positive z-score. Everybody okay? Kind of see it. There we go. According to 2016 Pew Research Center report, 73% of American adults have read a book in the previous 12 months. This estimate was based on a random sample of 20 American adults. Assume the conditions for inferences are met. Well, they're just telling me right now the conditions are met, so I don't even need to check them. That's what's nice when you see a problem like this. So if you see inferences are met, conditions check. You don't have to check each one of them, they're done. Determine the critical value for a 90% confidence interval. So I want a 90% confidence interval. I need the critical value for a 90%. So that leaves 10% left over. 10% on both sides, which means it's 5% on this side and this side. So I got to go to my trusty old calculator or in my table, exit, table, whoops, that's not this, that's this. That's not this one, it was this one. And look up 0.06. No, I'm sorry, 0.05. 0.05. 0.05, 0.04, 0.05, 0.05, 0.05, 0.05, 0.505, 0.0495. So it's right there somewhere. Negative 1.64. Or it's a whole lot easier to go in your calculator and do inverse norm and do 0.05. Let's go back to the left because that's what most people have. Negative 1.645. Negative 1.645, 1.645. Go here, go here, go here. Bam. Table A, 1.645. Inverse norm, 0.05 is negative 1.645. There's positive 1.645. If I want to look up 0.95, just recognize that, right? This is 0.05. This is actually the 95th percentile. That's the 5th percentile. That's the 95th percentile. Or if you happen to have a middle button, it'll give you both of them. Any questions about that Z critical value? All right. $16-point question on your test. Confidence interval. Let's show you how you get all your points. This is a 4-step process, so make sure we do all 4 steps. Understand their 4 steps are a little bit different than my 4 steps. So they have a 4-step process. I have a 4-step process. Theirs is a little bit different than mine. I'm trying to go off theirs. State the parameter you want to estimate and the confidence level. We are trying to find out the proportion of people in America that have a dog. We're trying to find out the proportion of cars in the United States that are white at a 95% confidence interval or level, either way. So state the parameter you want to estimate and the level. All right, next thing. Plan. Identify the inference. Check the conditions. Identify the inference. Check the conditions. In this chapter, our inference is going to be that one sample proportion Z interval. Our inference is going to be one sample proportion Z interval. One sample proportion Z interval. And then the conditions, are the randomness, the large numbers, and the 10%. Perform the calculations. Perform the calculations. It says if the conditions are met. Very seldom are the conditions not met. If the conditions are not met, they're going to ask you some type of a question that lead you to believe that they may not be, if that makes any sense at all. Like if they tell you to calculate and interpret, chances are really good the conditions are going to be met. If they're going to say, are the conditions met, chances are really good that one of them may not be. And then conclude. In context, in context, in context. Interpret. Interpret it. I can do this a lot better without anybody up here. I'm not even close to you, Ray. Just relax. Whoops. You're not there, sorry. You're not close to you. Do you feel the breeze? Do you? Ooh, cool. That's even better. She comes in late again.
What?
I said, she comes in late again. Okay?
Okay,
I understand.
I understand.
Okay. Okay, good. I use Sir Isaac Newton's philosophy of E equals mc cubed. It's something like that, isn't it? MC squared. MC cubed. M is the method. So that's where I'll just say 1 sample proportion Z interval, the method. The first C is the conditions. So that's where I'll say the conditions. The second C is the calculations. And the third C is to communicate the results or your conclusion, either one. I don't care which one of these you use, you get it all done at the same time. But you got to have the conditions, you got to have the method or the statement or what type of inference you're using. You got to show it to the calculations and you got to write the conclusions. 4-step process. 4-step process. All right, you ready? Let's see if we can do one of these. A recent poll, 738 randomly selected cell phone users found that 170 of them admitted to walking into something or someone while talking on your cell phone. Construct and interpret a 95% confidence interval for the proportion. They're going to tell you, guys. They're going to tell you what the proportion or means. It shouldn't be that confusing if we're doing a confidence interval or hypothesis test. It's an interval. Who would admit to walking into something while talking on their cell phone? Here we go. What do we need to do for this problem? Method. 1, samp, prop, Z, interval. That's my method. That's my method. 1 sample proportion Z interval. That's worth an E, P, or I right there if you say that. You say that, we've already got 1 point on this test. I make that 4 points. 1 point, 1 point, 1 point, 1 point. Next chapter, or I'm sorry, how about this? Next section, it's going to be 2 sample proportion Z interval. The next chapter, it's going to be a 1 sample mean. Then it turns into a T. That's a whole nother story. There it is, method. 1 sample proportion Z interval. And yes, guys, I'm perfectly fine. AP is perfectly fine if you want to abbreviate sample with sample and proportion with prop and interval with int. I'm okay with 1 prop Z int. 1 sample proportion Z int. That's my method. Now we want to check the conditions. What was theirs? What was the first thing? State? What's theirs for? State? I do that at the end when I do my state. Okay, conditions. Do we have a random sample? Random sample of 738 cell phone users. Check. We're good there. What's the next one we need? We need to prove that it's approximately normally distributed. So the first thing I guess I probably ought to do is find out what p hat is. P hat is equal to 170 over 738, which I think is 0.23. $738 times 0.23. 738 times 0.6777. This will be 170. This will be 600, 500, and 676. I think. Greater than or equal to 10. So the distribution is approximately normally distributed. Y'all okay on that? We're still writing. It's okay. This takes a lot of writing. Let's see what I got. A random sample of 738 cell phone users. Random sample, boy, I got that almost dead on. Oh, 10%. I didn't do the 10%. I was getting ready to do that one. I thought that was next. 738 is less than, you can't see my marker anymore, 10% of all cell users. What did that say? It is reasonable to assume that 738 is less than 10% of all cell phone users. Good enough. You don't have to state it like that. You just have to get it in there. What's the next one say? Large counts. The number of successes, 170, and the number of failures, 568, are both greater than or equal to 10. It should have said at least so the distribution is approximately normally distributed. I don't know why they didn't say that. I need to add that. I need to add that. I don't know why I look at the camera. I need to say it to the microphone. So I got my method. I got my conditions. Next thing I'm going to do is my calculations. I'm going to write the formula. P hat plus or minus Z square root P hat 1 minus P hat N. Sorry about my marker. And then I'm going to fill in the values. Oh, you can't see it at all. What was it? Is it 0.23? I think it's 0.23. 0.23 plus or minus 95%, 1.96. Square root, 0.23, 0.77, 10. No, I'm sorry, it's not 10, 738. 738. Now we'll go to our calculator, right? Punch all this crap up. End, exit, calculator, clear. Let me make sure that's 0.23 before I go on and do this. 170 divided by 738. Yes, 0.23. So here I go, 0.23 plus 1.96 times square root 0.23 times 0.77 by 738, enter. 0.26. Here's a little trick. Second and enter, and it brings all that back up. And you just backspace and turn that into a minus 0.199. Actually, I guess that's, they're not going to care. If you put 0.9199, and somebody else puts 0.2, and somebody else 9, and somebody puts 0.20, you'll all get full credit. Questions? You okay finding that value? You do not need to show anything from here to here. Use our calculator from here to here. So you don't need to show any of these steps here. Talk to me.
Where did you get 1.96 from?
Was the 95% confidence interval?
Okay,
That's a good question. You good?
yes.
You'll have that one memorized before too much longer. You will. Because that's by far the most common one. Calculate. P hat is 0.23. 0.23 plus minus 1.96 square root 0.23, 0.67. Should be 0.77, isn't it? 0.77. It's all right. Communicate your results. Don't shorten this. Don't change it up a whole lot. This is not exactly how you need to write it, but you got to have all these things in it. Fair enough? We are. I am. Whatever you want to say. 95% confident. We are 95% confident that the true proportion, you must mention the word true or the word population. You must mention the word true or the word population. We are 95% confident that the population proportion of cell phone users who would admit to walking into something or someone while talking on their cell phone, that's the context. It must be in context. Will be in the interval 0.20 to 0.26. You don't have to write it exactly like this, but you got to get all that stuff in there somehow. Okay, you got to mention the word 95% confident. You got to mention the word true proportion or the population proportion. You got to put it in the context and you got to put the values. Any part of that that's missing, they're going to dock you. If you don't mention the 95%, if you don't mention the population, you don't put it in context, you don't have to put the values. I guess if you put the values previously, will lie in this interval, you're okay. But context is big for them. Y'all know that by now. Questions? Everybody okay? It's not that hard. It's really not that hard. It's hard remembering all the stuff you got to do. That's what's hard. That's what's hard. All the stuff you got to do, it's kind of hard remembering all that. Like I said, on my test, I make that about 16 points question. About 16 points. Method is a point. I think I make that one sample, proportion, Z, interval. Random sample, proven normality, proving normality and saying it's normal, and then the 10%. And then I want the formula, and I want the values, and then I want the interval. And then I need the context of the problem, and that's worth about 3 points. So it's a lot of points just to get it. On AP, that's one question. There's 6 open response questions. Typically, that's one question. One question. So it's worth a lot of points. Yes, sir.
Ash, I wanted me to ask you, when would you use the confidence level instead of confidence interval?
That's a great question. That's what I'm getting ready to add on to. That's a phenomenal question. It's very similar to the one you asked earlier. So
Ashton asked that one.
okay. That's what I got. We got to make sure we fix that one. In fact, that's what I'm getting ready to talk about. I just want to make sure we're all on the same page right here. We're good? Okay. The most common mistake is that students think that there is a 95% chance that the population is inside that interval. And that is a mistake. It has nothing to do with a chance of it happening. We are 95% confident. Y'all okay with that? We are 95% confident that the true proportion is inside of here. Again, that has nothing to do with a chance. There's not a 95% chance it's in here. So let me talk to you about it like this. Many of you guys are getting ready to apply to school, and some of you have. Some of you got accepted to maybe some of them you may not have, right? Schools have an acceptance rate. Fair enough? So let's say that a school has an 80% acceptance rate. Is there an 80% chance that you are getting in? No, you're either getting in or you're not getting in. Right? There's not an 80% chance that you're getting in. You're either getting in or you're not getting in. Confidence interval is the same way. There's not a 95% chance that the population is inside of there. It's either in it or it's not in it. What does that mean? It means this. If I did this a whole bunch of times, 95% of those intervals will contain the true proportion. But we only did it one time. There's not a 95% chance that it's in this one. It's either in this one or not in this one. Let's kind of go a little bit further. End. Clear. Here is the true proportion. It's kind of hard to see, I bet. It's 0.65. That's that green line. That's the true proportion. I'm going to do a 95% confidence interval with a sample size of 30. That's my confidence interval. It actually got the population. Do it again. That one got the population. That one got the population. That one got the population. I can do this over and over and over and over again. Most of these are going to get the population. That one didn't. It's red. If I did it 25 times, whoop, it didn't do it. There it is. Here's 2 that didn't get it. 25 more, 25 more, 25 more. Right now, I'm sitting at 86%. Woo, that's pretty low considering I'm doing a 95% confidence interval. Over the long run, there, 91, 92. I'm not getting up to 95. It's messing up. But that should be 95% of them eventually. So I think Ash's question was, when do I use that one or when do I do that one? It's basically, this was calculate and interpret a 95% confidence interval. If they ask me to calculate and interpret, not to calculate, if they ask me to interpret the confidence level is when I have to state over the long run, if I did this a lot of times, over and over and over again, if I did this many, many, many times, if I did this 100 times, 95% of the intervals capture the true proportion. Can I help you a little bit? Or is it help Ashton? I don't know. He needs to let you know if it helps you a little bit. I guess he's live, huh? Oh man, good job. Did you get it?
Yeah.
All right. Sorry you had to miss some class for that, but
It's fine.
it is what it is. If I wasn't running YouTube right now and you guys weren't in here, I'd tell you what I really thought about that test, but I'm running YouTube right now and there's students in here, so I'm not gonna say what I really think about that test. You probably can infer it. Okay, again, that is the most mistake on this stuff, is it thinking that there's a 95% chance that it's in there. It has nothing to do with that. It has nothing to do with that. It's either in there or it's not in there. If I did this over and over and over and over again, I'd have a bunch of these intervals. 95% of the intervals will contain the population proportion. Okay? All right, you say yes or no or anything, or you didn't say anything?
Put a mind blown emoji.
He said what?
Put a mind blown emoji.
Oh, yeah. Well, that's not what I was looking for, but I get it. I can only imagine how you guys feel, because I went the first probably 7 years without really understanding that. That still doesn't make sense to me, how it's not a chance of it happening. But when somebody tells me it's either in there or it's not in there, and then they kind of, like I said, I had a student related to college entrances, and that kind of made sense to me then too also. Okay. All right, let's keep talking a little bit more. I want to make sure you understand a couple more things that I have tied into this. I'll do that at the end. All right, mind blown. Calculator. If a free response question asks you to construct and interpret a confidence interval, you are expected to do the entire 4-step process. That includes clearly defining the parameter, identifying the procedure, and checking conditions. Okay, make sure you do the whole thing. You have to get out of that, assess. That's really what we're looking for. This is what we're concerned about, right? But if you just put this down, whoo, you're missing out a lot of points. In fact, you're probably going to get 0 points for it. In fact, I have seen rubrics where you can miss this and still get full credit because you don't know how to work a calculator or something. Okay, remembering that interpreting the confidence level is different than the interval. This is the interval. I didn't write it down. The interval. We're 95% confident that the true proportion of whatever is between this interval. The level is, if I did this over and over and over again, I'd have a lot of intervals. 95% of those intervals contain the population proportion. Okay, those are big time difference. Interpreting the level. There it is. It's like college acceptance. I put that up there just to help kind of. All right, now, one more thing I want to make sure you guys understand is how the interval can fluctuate. How it can fluctuate. So I'm going to give you plus or minus 1 year. 1 year. You have to guess my age. How confident are you? 90%, 80%, 70%. Some of you might know you would be 100% cheaters. Let's say I give you 5 years. Now, how confident are you? Probably more. As that interval went from 1 to 5, your level went up. Because that z-score gets bigger. I didn't draw it up here. One standard deviation is 68%. Two standard deviations is 95, and that's a wider one. Let's say I give you 10 years. Now, how confident are you? I hope you're almost 100%, because the wiggle room is a lot more. So as that interval increases, your level increases. Hopefully that helps you make sense to that a little bit. On lesson 8.1, I think I talked about the basketball goal, right? In the swimming pool. If you can shoot into the swimming pool, you're probably 100% accurate. You're probably 100% sure that you can do that. The basketball hoop in the county fair, probably a lot less confident. As it decreased, our confidence level decreased. So there's a direct correlation between those, right? As the sample size increases, that interval will decrease, because our standard deviation will also get smaller on our sampling distribution. So as the sample size increases, my interval will also decrease. Those are big things that we should have gotten out of 8.1. You need to know how intervals fluctuate and how they can be changed. Everybody okay with that? I'm 50, by the way. Were you close?
No. Thought you were pretty young.
Oh,
Yeah.
brown noser.
I mean, I was being serious.
You were?
Yeah.
You wouldn't have guessed that?
Yeah, I was like gonna get like my highest number was like 48.
Oh, yeah.
Yeah.
You're the man, right? I knew I liked you for a reason.
Yes, sir.
I used to do that. I used to give a piece of paper anonymous and collect it and then get an average of that, right? So I would have an X bar value, and then we would get a confidence interval and see if we captured it or not. I don't do all that stuff now because I just don't have time, but actually I probably do. It's a bad sample. It's a pretty small sample. N times P is not going to be greater than, of course, that's not a P. All right. Last thing we need to discuss in 8.2. In planning a study, we might want to choose a sample size that allows us to estimate a population proportion, giving a margin of error. Okay, kind of like we did in chapter 7, where we had wanted to choose a certain sample size to give me a certain standard deviation. Now we want to choose a certain sample size to give me a standard margin of error, or a certain margin of error. The formula for the margin of error is everything after the plus and the minus. It's everything after the plus and the minus. So they call it ME. I always called it MO. It's the Z score and P hat, 1 minus P hat, N. Okay? And guess what they're going to give us? They will give us the margin of error. They will tell us what. If they don't, we'll use 95. But here's the issue with this one now. If I'm trying to predict the sample size, that means I haven't taken a sample yet. If I haven't taken a sample yet, I don't have a P hat yet. If I don't have a P hat yet, what in the flip am I going to put in for that P hat value? See the dilemma? I haven't taken a sample yet. If I haven't taken a sample, how the heck, and the reason why that's not P is because that would be the population. If I know the population, there's no reason to do any of this stuff. We don't know the value of P hat until the study has been conducted. Well, after the study has been conducted, I want to know the sample size prior to doing that. This means we have to guess the value of P hat. Well, we don't want to guess the value of P hat, because if we guess, that means we're just taking a bad guess, and we're probably wrong anyway. This is what we want to do for the value of P hat. One of two things. They will tell you a value for P hat because of past experiences, or there's some pilot or preliminary study, something like that. Very seldom does that happen. If they don't tell you anything, you're going to use 0.5. You're going to use 0.5. And the reason why you're going to use 0.5 is pretty simple. Once you think about it, 0.5 times 0.5 is 0.25. 0.6 times 0.4 is 0.24. 0.7 times 0.3 is 0.21. This number is slowly getting smaller. And even if I flip-flop that, that's 0.4, 0.6. By using 0.5, we are using the worst case scenario. It's the highest that could possibly be. This number up here is the biggest it could possibly, there's no way that this number up here will be any bigger than 0.25. 0.25 is the absolute biggest that will ever possibly be. There's no way to be any bigger than 0.25. So we are using the worst case by using 0.5. Everybody okay? Let's see if we can do this problem. And then we're going to call it quits. A company has received complaints about its customer service. Users intend to hire a consultant to carry out the survey of the customers. Before contacting the consultant, the company president wants some idea of the sample size that they will be required to pay for. One value of interest is the proportion of customers who are satisfied with the company customer service. She decides that she wants to estimate to be within 3 percentage points. So that's my MO. My MO will be 0.03. 3 percentage points. 5% confidence level, 1.96. Square root, how large of a sample is needed? They didn't tell me anything else, so I'm going to use 0.5, 0.5, and N. And now it's your math to find out what N is. Finally, you get to use a little bit of algebra 2 that you're supposed to have for this class in order to take it. Divide both sides by 1.96. Sorry. Less than or equal to. It's okay. Other way around. I'm sorry. It's okay for this to be smaller than 0.03. We don't want it to be any bigger than 0.03. Divide both sides by 1.96. After I divide by 1.96, I need to square both sides to get rid of that radical. After I do that, I need to multiply both sides by N, and then divide both sides by whatever the heck 0.03 over 1.96 squared is. And so it looks pretty darn bad, but we also know that 0.5 times 0.5 is just nothing more than 0.25. So it'll be 0.25 divided by whatever the heck 0.03 divided by 1.96 squared is. And I think they're going to get something like 1067.11. Which means we need to sample 1068. Because just like last chapter, we cannot round it down. You have to round it up to the next person. This sample needs to include 1068 customers. Why do we not round down? Because it possibly may not get to the 0.03. That's basically it. A smaller sample size is going to make a larger margin of error. I don't want that. I want a smaller margin of error, therefore I need a larger sample size. If that was multiple choice, it probably wouldn't be 1068. It'd probably be something like 1070, maybe even 1080. But you would use the smallest one that was closest to the 1068 without going under. Woo! A lot of stuff. I hope Hope you can state and check each condition. There's 3 conditions. Hopefully you can state them and check them. Hopefully you can determine the critical value from a confidence level. That's found in that Z score. Hopefully you can construct and interpret a confidence interval from some kind of population proportion. Hopefully you can find the sample size that is needed to give me a certain margin of error. Woo! Yes, no, maybe? I won't see you guys for another week, right? I won't see y'all for another week. On Wednesday, I'm going to do 8.3. That should probably take 15 to 20 minutes because the only difference between it is 1 sample and 2 samples. And it changes a little bit of the formula, and there's a couple of things we need to know. Friday is a B day, so you guys do not have to worry about the Friday. Monday, I'll see you guys back. I do not know if we're going to continue this same process or not yet. I do not know when that decision is going to be made. My guess is that decision will not be made until Friday afternoon at the possible latest bit because that's what they do to us. Yeah, you can play that. Either way, I'm going to see you guys on Monday. More than likely, that will for sure be, I would call it a work day, but I do not think I'm going to test over just this chapter. I think I'm going to include next chapter and just give 1 test, I think. I'm to crunch time now where I want to make sure I get all the stuff in. And who knows what's going to happen at spring break or after. So we're getting close. Y'all okay? If you've got any questions between now and then, I would like for you to send me an email, or if you want to text your buddies, like when I'm in front of the classroom and running the live show, if you want to text it then, you're more than happy to. Whatever you think I can do to help you guys out while you guys are not around this classroom. I'm hoping that this is the best way that I got. If you think there's something different or better, please let me know. Or if I can just help you or whatever I can do. It is what it is. That being said, let me stop this thing. Oh, I forgot. One more thing I want to show you. I forgot. This is going to save you a ton of work. Hope y'all didn't hang up yet. If you did, all right, here. Your calculator will calculate all this stuff. So me showing you that second enter button, I can save you about 15 more steps. Stat, this button here that you're going to wear out. Stat. We don't want to edit it. We don't want to calculate. I need to go over to tests. Okay, so go over to tests. Test, interval. Oh, I went over. 1 prop Z interval. That's your method. So that's even nice because, oh yeah, I need to write that down. That's one of the points that you're going to get. So I do 1 prop Z interval and hit enter. X. I think that's the right stuff. I think it was 170 out of the 738. And I want a 95% confidence interval. And I go down to calculate and I hit enter and there it is. So it does all that mathematics for you. Fair enough? So your job is now just to write the formula, write the values, and then write this number. And then it also tells you p hat. Y'all okay? So your calculator will save you about 15 to 20 steps. Well, I'm stretching it just a little bit, but it'll save you a lot of work to have to do it. Okay, 1 prop. It's different than the Z interval. Don't do the Z. 1 prop Z interval. Okay? All right. That was what I about forgot. I can go here, and I can go here, end it. I had a